What makes a magnet a magnet? Why are some materials affected by an invisible force whilst others can care less? Is every magnet the same? Let's start with what a magnet is. A magnet is a material that is able to create a magnetic field. A magnetic field produces field lines that always go from the North Pole to the South Pole of the magnet. When a magnetic material is placed in a magnetic field, the material will try to align itself with the field lines of the applied magnetic field. This gives us the phenomena of magnetic attraction and repulsion. The ease with which the material aligns itself with the magnetic field is called a material susceptibility. The easier the material is to magnetize, the more susceptible it is. But why does a material produce a magnetic field? Let's take a look at an example where the material is irrelevant, a wire. A wire with an electrical current passing through it produces a magnetic field. This is due to the movement of electrons through the wire. We can apply the same principle to individual atoms. Movement of electrons around the atom produces a magnetic field. We can therefore think of individual atoms as tiny bar magnets. This is a magnetic dipole, also known as a magnetic moment. If there is only one valence electron, the magnetic moment created by the spinning electron is in a certain direction. If, on the other hand, the valence electrons are paired, the magnetization induced by one electron is cancelled out by the magnetization of the other, giving us no net magnetization. There are many different types of magnetism, but the most common one found every day is ferromagnetism. Ferromagnets come in many different shapes and sizes: bar magnets, fridge magnets, to cuboidal and even cylindrical. In a ferromagnet, we get spontaneous alignment of magnetic moments, giving the material a net magnetization. Paramagnetism is a different type of magnetism to ferro. Paramagnetism occurs when the material has a lone valence electron, like aluminium. The material will exhibit a weak susceptibility and is always attracted to the applied magnetic field, regardless of whether it has a north or south pole that is applied to it. All the magnetic moments are randomly aligned. When a magnetic field is applied, the moments align themselves to the field. Paramagnets can't induce magnetism in other materials because the moments are not aligned until a magnetic field is applied to it. Diamagnetism is basically the exact opposite of paramagnetism. Diamagnets have paired valence electrons and are always repelled by an applied magnetic field. Bismuth and water are good examples of a diamagnet. Diamagnetism occurs due to Lenz's law, which states that a current induced by a magnetic field will induce a magnetic field that opposes it. This same principle occurs on an atomic level in a material, with an induced current in the material inducing a repelling magnetic field. Now that you understand some basics of magnetism, let's move on to something a bit more interesting: ferrofluids. Ferrofluids are tiny magnetite particles covered in a surfactant to stop them sticking to each other, suspended in a carrier fluid like water or oil. Magnetite is just an oxide of iron. When a magnetic field is applied, the magnetic particles are attracted to the field and pull the liquid along with them, giving us a mass movement of liquid. Ferrofluids work because the magnetic particles are so small. Normally, magnetite, being made of iron, is ferromagnetic, and as a result can be attracted or repelled depending on the applied field. Ferrofluids, on the other hand, are always attracted to the applied field, like a paramagnet. The magnetite in a ferrofluid is less than 10 nanometers in radius. To put this in perspective, visible light's wavelength is between 450 and 700 nanometers, and a human hair is several thousand nanometers in diameter. At this tiny size, room temperature provides enough energy to keep the magnetic moments constantly flipping between north and south in the magnetite. The ferrofluid, therefore, doesn't create a magnetic field because there is no net magnetization. There can't be, since all the magnetic moments in the particles are constantly flipping. When a field is applied, though, the ferrofluid is attracted because the applied field causes the magnetic moments to stop flipping and be aligned. What makes this interesting is that this attraction is far stronger than normal paramagnetism, so we call it superparamagnetism. Before we discuss some applications for ferrofluids, let's have a look at where they came from. Ferrofluids were originally invented by NASA in the 1960s as a way to move rocket fuel around a spaceship in zero gravity. Pumps don't work in zero gravity, so they hoped that magnets would be able to move the fuel about. However, they ran into a couple of issues. Firstly, all the tiny magnetic particles still added weight, and in a spaceship, every gram counts. Secondly, the magnetic particles in the fuel contaminated the fuel and ruined the combustion, meaning that they produced less thrust. This meant that the fuel was heavier and produced less thrust, making it basically useless for space travel. Thankfully, they stumbled across solid rocket propulsion and soon shelved the ferrofluid idea. However, other scientists saw its potential. A major area of research is in using ferrofluids as a drug delivery method. The magnetite particles are non-toxic to humans, making ferrofluids the perfect vehicle for targeted drug delivery. The ferrofluid, with the drug we wish to administer, is ejected into the bloodstream, and then magnets can be used to get the drug to exactly where it's required in the body. This allows for targeted drug delivery, which is quicker and more efficient than waiting for the body to digest the drug and circulate it around the body. Ferrofluids are also finding applications in speakers as dampeners. The ferrofluid achieves two goals simultaneously. It acts as a sealant and as a dampener. The fluid can be held in place with a magnet. This creates an airtight seal, which stops dust getting into some of the more important electronics in the speaker. It also allows the speaker coil to move through it without friction. This improves the sound quality since less kinetic energy of the coil is lost. The upside to this improved efficiency is a clearer and louder sound, which means that speakers can be smaller without compromising on quality. Sony are already in the process of producing such speakers. Hopefully now you understand a bit more about magnetism and ferrofluids. Thank you for watching.